My name is Matthias Noack. I'm head of development here at PLS Development Tools, and today I'm going to show you some features of UDE for debugging multi-core high-end SoCs based on Cortex. For our demonstration, we are using today a high-end automotive multi-core SoC from the STM Stellar family. This SoC consists of several different cores. It's a heterogeneous multi-core system. It has 6 Cortex 52 cores, 2 Cortex M4 cores, and a huge on-chip memory. We are using a sample application that is running on that target processor. We have, in the end, 3 different applications. One is running on the R52 cluster, running an ARM version 8 R profile, and this application boots up the whole system and starts up all the other cores. On the Cortex M4 cores, there's every Cortex M4 core and a separate demo application is running with ARM version 7, SUM2 instruction architecture. We have several L files, and I will show you how to load them in the debugger and debug this system in a multi-core manner. The demo board on the desk looks like that. We have connected one of our universal access device UAD2Next with Ethernet and USB 3 connection to the target board, which is an evaluation board for this STM Stellar controller. The UAD2Next is connected with an SWD adapter to the target and via a serial trace cable to collect the trace output of the Aurora multi-gigabit high-speed trace. Okay. When I'm going to show you a short demo, we will use UDE, and the central point of using our tools is the workspace. This workspace consists of the target configuration, which is a description of the target that's actually connected, the number of cores, initialization scripts, memories, and so on. Then we have binary files, which are the application and symbols of the application, the debug symbols that are executed on the target for the debugger to have the information about where the variables are located, where the functions are, local variables, lifetime information, and so on. Then we have for sure this access device, which is doing the physical connection to the target system, and then within our workspace we have several views where you can have a look into your target system, in the memory, in the variables for the registers, and analyze windows for statistical and trace information. We will see in the demo. The setup of such a workspace is quite easy. UDE more or less guides you through the generation and with a graphical user, easy to use graphical user interface. UDE in general looks like that. We have a main window, and in this main window we have every view for every core included. So we have one user interface for the overall system. With our latest UDE 2021, we have completely developed new user interface. We are using a new framework, especially made for debugging high-end multi-core SoCs to keep the view of them. The different views in the UDE window are distinguished with coloring. So we have a dedicated color for each core, so you can easily put them together, and you have an easy overview about which window belongs to which core. Within the user interface, we have several features then for the runtime debugging of your application. We can synchronize break, step, and go. We can use multi-core run control groups where we can put the cores together, and we can use multi-core breakpoints and so on that I'm going to show you in the demo. Besides, let's say normal debugging, we have also this trace support in UDE. In the Cortex, ARM Cortex world, we are using the core side debug and trace infrastructure. And here we are supporting every of these existing trace clients and trace sources, like the ETB or TMC for on-chip memory trace, like the HSSDP for this high-end, high-speed multi-gigabit Aurora trace, or the good old legacy TPRU-based parallel trace. What can we do with the trace information? We can show that in a window, so you can so you have an overview about what was or what's actually executing on your target system. Then we can do some many analyze operations on this trace information. For example, a call graph analysis or the visualization of the program window of the program execution. Or performance analysis, and for sure code cover analysis for your ISO certifications. Okay, this was a short overview about UDE and what we can do. Let's start with a demo. Here I have opened the main window of UDE 2021. We are starting from scratch, creating a workspace, loading some applications, and doing debug stuff. So first we create this workspace. We click here on new workspace. We name it anyhow. And then UDE asks for a target configuration. This configuration file consists all this information about the target. We have a huge number of predefined configurations for nearly any board and controller that we are supporting. For our demo now, we take one out of the Stellar predefined configurations. We take this SWD configuration. It will be checked out. I must not do this here because it's already there. So I click on cancel, and then I'm going to select it. And then UDE asks the next question, which is that I need to select the course that I want to debug, or means that I want to see in my workspace. For our demo, we use the first Cortex R52 course and two of this M4 helper course. Okay. After some short seconds, connection to the target system is established. The UID to next has connected to the Stellar system, and we can see here in the message view that it was successful, and we can see that we have 4 cores now connected. One is halted after reset. This is a green core here, that's core 00, and the other cores are in an inactive state, which is here normal, because all these cores needs to be woken up by the running application. And that's what we want to do now. We want to load our applications that are running then on the target system. We have, as I said before, 3 different applications. One is running on the R52 course. It's called the Multicore demo. Select the hex file, and then we select 2 additional ELF files for our helper course. The first and the second one. And now we can see here in this multi-core, multi-program loader that UDE has these 3 files, is aware of the 3 files, that now we can select which file we want to download, or from which application file we want to take which information. We have the choice for a binary and symbols information. Symbols mean that that UDE does load only the symbol information out of the ELF file, and the blue option binary means that the patterns to be downloaded are loaded by the debugger. In our case, only the multi-core demo needs to be downloaded to the target because it consists of any of the other binary patterns, because it's loading them. For the 2 helper time demo helper applications for our M4 course, we just need to load symbols that we can debug and set breakpoints and debug and step through the code. So in this case, we are doing the options like this, clicking OK. Then UDE loads the ELF files, analyzes the symbols, and do the target download. And now the next dialog is opened. This is add in memtool dialog, because UDE has detected that there shall be something downloaded into the on-chip flash. In this case, we have a PCM memory, a phase change memory, is a quite new and fast technology from STM. And our flash programming tool will handle all this programming. We just need to click on Program All. Then the patterns are programmed into the modules, and a verification is done. So, and this says OK. So that means everything has been loaded now, and we can start with our debugging. Okay, close this window. And now, after we have prepared everything, we can just start our target. We click on the Start Program button, and after a moment, all the cores are changed their status into running state. In the background, what happened? UDE has started the cores, and the running application has booted all the other cores, and they are running now. So now I can start my debug task. I can now, for example, just and break, and we see that every core has halted now, and I can do now stepping or setting breakpoint for our debug tasks. When I'm doing this run control operations like go and step, not only the core that has a focus is stepped, but actually every other core is stepped as well. That means the cores are started and stopped synchronously by UDE. And this is done because we have a so-called run control group, which is predefined here, where we can see every core is included. And that means when we do a run control operation like go, like step, step over, step into, whatever, all the other cores are started and stopped at the same time. This is done by using on-chip hardware, on-chip debug hardware. In this case, we are using here the available cross trigger, the core-set cross trigger that are available in nearly any Cortex SoC. Okay. The next, I'm going to show you how to set up a simple trace for this high-end multi-core SoC. We keep the target running for now, and we open the trace window. And this is empty as per default because nothing was ever collected. So we need to configure first the trace to see or to make some trace snapshots. For this, we simply click with the right mouse click to the context menu and selecting trace config. Now the configuration dialog opens. We have several configuration pages for every trace client that is existing and supported on the target. First, we do some general settings. We are using as a so-called capture device the core-side trace memory controller for on-chip trace. It's available on the target. We reduce a little bit the trace memory here. This is enough for our demonstration. And then we configure a simple trace for the core 0. We configure code and data trace, and we enable some timestamps, so we have timing information and we can do timing analysis. So that's all. After configuring, we just start the trace with the context menu, start trace, and then the trace clients, the core side infrastructure is configured by the debugger and the trace is started. And we can see here in the status bar that there's something collected. The on-chip trace buffer is configured as a FIFO, as a ring buffer FIFO. So we have the oldest data is overwritten and we have only the latest, the newest one. Okay, to stop the trace, we simply need to stop it. And after a while, UDE has analyzed the trace output. And here we can see what we have traced. In this case, we can see the instructions and the source code, what that has been executed. And in case of load or store instructions, we can see the data that has been actually loaded or stored here. This is more or less an endless loop, but we can check if there's anything, if there's something special happening during our trace. For this, we can open the execution sequence, the so-called execution sequence window. And here we have an overview about what has been executed on the target, and we can see that about all the time our program is running in a function called main, which is quite normal because our application is only triggered from time to time by an interrupt. Here, as you can see, there has something happened, something interesting. Let's move into there, and we can see that here the program flow has changed to some other functions, and it looks like that we have here some kind of interrupt. This is okay. Our application is interrupted every millisecond from an interrupt. We can make a short check here. We can see that we have here and here such an event, and we can measure the time, for example, with a marker 1 and marker 2. And here in the bottom, we see that the difference between both markers is nearly 1 millisecond, which is correct. Okay. As you could see, the configuration of the trace is might be a huge dialogue depending on the number of trace clients you have on your target, and it could be very, very complex here to have an overview or to have a to understand this. So for that we have developed an additional add-on, the UEC, Universal Emulation Configurator, which is a quite cool feature where you can configure your trace task in a graphical manner via drag and drop basic blocks. I'm going to show that to you to set up a more complex trace task. First, I need to switch to this UEC add-in. We change the so-called configuration level from dialog to graphic. Okay. And now when you open the trace configuration and separate, a new window is opened, which looks like this. Here we have we can select from a bunch of predefined configuration items to drag and drop our dedicated trace tasks. We have an init block where we can do all this general settings that we have done before in the dialog configuration as well. And now we will take one of these predefined blocks and actions on instruction address range. Let's do a trace task where we make a trace only from one function. We take, for example, the core 01 at this time, and we will select a function. Let's take this main worker A here, and we want to trace from the beginning until the end of that function. We make an inclusive range. It means only this function is traced, not nothing else. And we want to see the code trace for this. Okay, that's all we need to do to configure a code range trace. And then let's do this trace. Start it like before and stop it after a while. And we can see now the color has changed because I have traced a different core. And when we have a look in the function column of the trace window, we see that only our function main worker R is there. That means only trace for this function has been collected. What can we do with this trace information? For example, we can analyze the code, the coverage of this function, which is a good feature for your ISO certifications, for example. For this, we can open the code coverage analyze view. This has been completely reworked in UDE 2020 to be more flexible, more user-friendly, and faster. And let's start the analyze. And after some moments, the analyze has finished, and we can see the code coverage of our trace snapshot. Oops. And we can see here the calculated code coverage line. This coverage is based on this trace, so it's non-instrumental, which is quite important to check the code of that's really running. Here we can see, for example, that these two lines here, there's a coverage of 0%. That means they have not been covered, and the user, the developer, can now go ahead and look into what if this is an expected behavior or if there's an issue, and so this information can be used for the developer to improve the behavior. Okay, that is all for now for this short demonstration. What have we shown here? You have seen that we can set up an initial UDE workspace quite easy using the guide of Universal Debug Engine and the graphical user interface. We have downloaded a complex target application consisting of three different compiler outputs. And we have seen that we have configured trace and then a more complex trace configuration very quickly. So you can use and go ahead very quickly with our tools.